In this example, we have a resistor network consisting of 3 resistors, and 2 of these are clearly in parallel. That's R2 and R3, and then that parallel combination is in series with R1. So the first thing we want to do is to simplify the circuit down to one equivalent resistance. So the way we proceed is to combine those 2 that are clearly in parallel. 1 over Req is 1 over R2 plus 1 over R3. And if I plug in the numbers here, that's 1 over 8 plus 1 over 5. I like to do these all at once in my calculator. So I do 1 over 8 plus 1 over 5, and I press enter, and then I do 1 over that result to get the reciprocal. In this case, it comes out to 3.08 ohms. Okay, next we redraw the circuit with the equivalent resistor in there. And now my circuit is just a simple series combination of 2 resistors, and the resistances just add. So again, I'm going to use this arrow notation. I'll just kind of generically write R1 plus R2. I don't mean the original R2 in the circuit. I just mean add these, and I get 13.08 ohms. So I redraw the circuit again, and I'm down to the simplest possible circuit. So I just have my power source and my 13.08 ohm equivalent resistance. Once I get my circuit boiled down to a single resistor, it's really quick to find the total current. So I'm just using Ohm's law for this, and I'm going to say I equals V over R. And this equivalent resistance has a potential difference of 3 volts across it, and R is 13.08 ohms. And I find that my total current is, just keeping 3 sig figs, 0.229 amps. So then I start to work backwards through my circuit, and I'm going to use the fact that in a series combination, both resistors have the same current through them, and that's the same as the current through the equivalent resistance. So I bounce back to my second picture, and I go, okay, each of these then has a current of 0.229 amps going through it. That allows me then to find the voltage drop over each of these resistors. And for that, I use Ohm's law, V equals IR. That's 0.229 amps multiplied by 10 ohms for this top resistor, and that's 2.29 volts. For the bottom resistor, it's going to be 0.229 amps multiplied by 3.08 ohms. And if I just round to the same decimal point, that's 0.71 volts. And let's go down and just address the questions below real quick. I already took care of A. In fact, almost all the work that we're going to do is going to be up in the circuit diagram. Okay, so I've got I total is 0.229 amps. I did intend to present all the quantities in this problem to 2 sig figs. My circuit drawing software wouldn't allow me to show the 0.0 on there, but if you wanted to express this to 2 sig figs, it'd be 0.23 amps. Part B, compute the voltage from A to B and from B to C and verify that those 2 add up to 3 volts. So if I look at my nodes in the original diagram, going from A to B is just, that's the voltage across R1 or the 10 ohm resistor, and I just figured that out. It's 2.29 volts. How about from B to C? Well, I'm just going to use the fact that the voltage across the equivalent resistor from a parallel combination is the same as the voltage across each of the resistors in the parallel combination. And I just computed that as 0.71 volts. So if I go back and write that in the first circuit diagram, it means I have 0.71 volts across the 8 ohm resistor, 0.71 volts across the 5 ohm resistor. It means that VBC is equal to 0.71 volts. And if I look at the sum of these 2 voltage drops, it should be equal to the terminal voltage of the battery, because going from A to C gets me all the way from the high side of the battery to the low side, and indeed, this comes out to 3.0 volts. In part C, we're asked for the current passing through each resistor, and we want to verify the current entering node B is equal to the current out of node B. So all the current in the circuit travels through R1, so I'm going to use I total for that. And we already have a number on that. It's 0.23 amps. When I hit this node coming into the parallel combination, that's going to be split. I'll call that piece I3 and this piece I2. But I've already got the potential difference across each of these resistors, and I have their resistance, so I should be able to figure out the current using Ohm's law. So I is V over R. I2 is going to be equal to 0.71 volts over the size of that resistance, which was 8 ohms. And I get 0.089 amps. Across the 5 ohm resistor, again, I is V over R, and I get 0.14. I'll just keep an extra decimal just for a second. 0.142 amps. So I'm just going to verify real quick that all the current entering node B is equal to the current exiting node B. So I know the current entering is I total. I've already got that. That's 0.23 amps. So if I check I2 and I3, that's 0.089 amps. Added to 0.142 amps. And if I add these and round to 2 sig figs, I do get 0.23 amps. Again, that's equal to I total. So that's good. Finally, in part D, I'm asked to find the power dissipated by each resistor and then the total power dissipated by the circuit. So then I want to compare that to the power I would get by just looking at the equivalent resistor in circuit number 3 up there at the top. So let's just do that power calculation real quick. I guess I'll color code this since we're getting a little bit crowded. All right, so when it comes to power calculations, the most fundamental formula for this is IV. But if you start doing substitutions with Ohm's law, you can write it as I squared R or as V squared over R. So you got choices. In this case, I'm looking at a 3-volt battery, 13.08 ohm resistor. I could get into the current if I wanted, but then I'm risking compounding rounding errors. So I'm just going to go with V squared over R for this. So this will give me the total power dissipated by the circuit just by looking at the equivalent resistance. And it's V squared over R, so 3 squared over 13.08. And I get 0.69 watts for this. So we've actually answered the second question in part D first. I think for the others, I'll go ahead and use I squared R just as a way of mixing it up. So P1 is going to be I squared R for this resistor R1. And I is 0.23, so 0.23 squared. R was 10. And I get 0.53 watts. Then I look at P2. Again, that's I squared R for the resistor R2. And I have I is 0.089. Square that, multiply by R, which is 8 ohms. And I get 0.063 watts. Then if I look at P3, I have a current of 0.142 amps passing through that resistor. Square that, multiply by the resistance, that's I squared R, and I get 0.10. When I add all of these up and round to 2 sig figs, I get 0.69 watts. So it checks out. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.